This is Knowledge Engineering with Semantic Web Technologies. This is part 7 of Lecture 1, Knowledge Engineering and the Web of Data. And in this part of the lecture, we will talk about RDF, the Resource Description Framework, and how to represent simple facts of knowledge with RDF. So RDF is one of the main building blocks of the Semantic Web Technology stack. It's here in the information exchange layer. Every information you exchange here in the web of data, you encode with RDF, the Resource Description Framework. How to do that? Let's look at a simple example. So you might remember from the previous parts of the lecture, planet Pluto. So how do I represent the following fact? So let's consider the fact Pluto has been discovered in 1930. How should we represent this, for example, with a technology like XML? You all have heard about XML. So one possibility would be this. So I think of a tag which is called discovered, and within the discovered tag I define another tag which is called discovery, and there I put Pluto, and I put also a year in it, which would be 1930. Yeah, sure, this would be one possibility. But I could also think of another possibility. So here, for example, I could define a planet which has a name Pluto. So I define name as an attribute. And then I define a new tag, year discovered, and say this is 1930. Or I can abbreviate it even further. I can say I define a planet with two attributes, with a name and a discovered date. So the problem is, of course, all of these three are somehow correct. They are valid expressions, well-formed XML expressions. But it will be difficult to compare them and to identify them that they really represent the same information. So the main problem here is there a unique or intuitive way to model knowledge in XML? And I can tell you no, there is not, because there's nothing like a so-called normal form for representing knowledge in XML. So XML is not really well suited. And this was the reason that for knowledge representation, people had to think of other possibilities than this simple standard known from software and data engineering. So what you could do, nevertheless, if you have two different XML representations, of course you can translate them from one schema into the other schema. You can do this via so-called XSLT, which are XML style sheet transformations. So this, of course, is possible. But of course, it's very, very difficult, because for each possible schema, you have to define a transformation forward and backward. So therefore, the representation language for knowledge should be on a more abstract level that does not take into account different XML schemata. Okay, back to the fact Pluto has been discovered in 1930. How should we represent this in a more or less intuitive way? So let's look at the fact here. So we are talking about a subject. The subject is Pluto, the planet. So we say something about that planet. So this is kind of a predicate. So it has been discovered at a certain time. And of course, we give in the end an object, which is a value we assign to that predicate. It's 1930. So this is a nice structuring of the fact we see here. So we have three parts: subject, predicate, and object. And this, of course, if you're looking for a representation, could simply be represented with the help of a graph. So an intuitive knowledge representation of simple facts, as you see here, could be with the help of a directed graph, which means Pluto, which is a node, has been discovered, so the predicate is an edge, and the date, 1930, is then the object. So this would be a rather intuitive way to represent this kind of knowledge. And the Resource Description Framework, RDF, adapts exactly this concept. So what does RDF mean? So we are talking about resources which can be usually everything. And as we already know, everything, every object from the real world or also abstract concepts can be identified and referenced via a URI, a Uniform Resource Identifier. So then there are descriptions, which means description of resources, and we do descriptions in RDF by representing properties and relationships among the resources, and we do this representation as graph. And then, of course, this is a so-called framework, which means it's a combination of web-based protocols which are involved. So we have URIs to reference and identify things. For access mechanism, we have HTTP. And then we have certain so-called serializations or dialects or encodings of that RDF, which can be based on XML, which can be Turtle, or which can also be based on JSON, and many more. So again, what we need to work with this as a knowledge representation, we also must have a so-called formal model. So we will talk about that later on. So, general knowledge in RDF is expressed with a so-called list of statements. And these statements, these RDF statements, are all organized in the very same manner. They follow the same simple schema. They are so-called RDF triples. So, 3 parts: subject, predicate or property, object. Pretty simple. So here again we have this basic intuitive schema. So what we can do, of course, we can express the subject, planet Pluto, with a URI. For example, with a URI we know from DBpedia. Then, of course, we could also express the predicate, or the property, has been discovered in, by using a vocabulary which can be addressable and accessible via the web with the help of a URI. And then we have the value, the object 1930, which might be represented then as a URI if I talk about other resources, or as a literal, which might be here, for example, a character string or a value or a date. So URIs and literals here are the basic building blocks of RDF. And an RDF statement or an RDF triple always follows this 3-part structure, which means we have a subject expressed as a URI, followed by a so-called property. Here we are talking about property, not about predicates, because predicates are used then for natural languages, and this is a formal language. So we have subject, property also expressed as URI, and then this property must get a value somehow or must reference an object, and the object then is represented as URI, or an object value is represented as a literal. And again, we have here the RDF building blocks, URIs and literals. And in the gray box here, you see, for example, one of the many serialization formats of RDF, which is the so-called N-triples serialization. And we will talk about this kind of serialization later, but you see here that the subject, so planet Pluto, and the property, discovered, are expressed with the help of vocabulary or URIs that come from DBpedia. And then 1930 is expressed as a literal, which is here a character string. And this denotes nothing else but the graph that is depicted here below with nodes and edges. So we have URIs and we have literals, which means we have 2 different things that can be connected within an RDF triple. So if we are talking about URIs as an object, we always reference a unique resource, a unique object, which has itself an address, which means it exists. On the other hand, literals describe only data values. And these data values do not have a separate existence. So they are only a value. You see that here in that example, we have here a small graph representation of the RDF facts that Pluto has been discovered in 1930. 1930 here is a literal. And Pluto has a discoverer, so that's the person who has discovered Pluto, and this was Clyde Tombaugh. And Clyde Tombaugh also has a DBpedia URI, so it means this is a resource which can be identified and referenced over the web. So we have here, on the one hand, an RDF triple with URIs as object, and we have an RDF triple with a literal as an object. So these are 2 different ways to express knowledge with RDF. So when we are looking at literals, literals, of course, can be more than simple data strings. So these values can have a data type. So they can also be, for example, numbers. And I can distinguish between, let's say, integer numbers, floating point numbers, and all what is available as a data type. So what we are using here, for example, are the so-called XML schema data types, which belong to the XML schema definition. So you have here a namespace. You probably know that already for XML schema. And there are lots of data types defined. You can see them here on the right side of the page. And we have a few examples. So here we have the example semantics, and semantics is a character string. To denote or to represent a character string explicitly with a data type, usually the literal is expressed here in double quotes, as you see here, and then follows the address of the data type within the namespace. So it's the string within the XML schema namespace. Or the next example that you see here, that's a floating point number, 1161.00. So this is a floating point number. Or the next example is the date. So this is the 2nd of August 2015. And this is an XML schema hash date. So with the help of this XML schema data type namespace, you will be able also to express data types with literals, which gives or provides additional semantics. If we consider strings, we also have the possibility to denote the language in which they are encoded. So there are these 2 character identifiers that follow a certain ISO standard. So for example, I could say semantics, and this is encoded in English. So then there follows this %en for English identifier, or I can say in German semantic, which then is followed by an ampersand and de for the German language identifier. And there are many more. You can look them up in the material for the lecture. So we distinguish in XML between untyped literals, which do not have explicitly a data type assigned, and we have so-called typed literals, which comprise also a data type. And there is one specialty among URIs, which are so-called blank nodes. So among all things that can be addressed via URI, there is also something, or let's say some node in an RDF graph which does not have an URI, but which can nevertheless also occur as a subject, for example. And this is a so-called blank node. This is a node without an URI. So what does that mean? So this means, if you simply look at that graph, that there seems to exist something which has been discovered in 1930. We do not know what has been discovered in 1930, so this is an empty node. And on the other hand, we also know that this thing has been discovered by Clyde Tombaugh. So this is a very nice feature with which you are able to denote existence of an individual with specific attributes, but without providing an identification or reference, which also means that, of course, nodes like that never can be accessed from outside because they lack an identification. They do not have an URI. But sometimes it might be useful to apply or to make use of nodes which do not necessarily have a URI. So if you simply want to state that there exists something which has certain properties, then you can make use of that specific concept and structures. And these nodes, without having an URI, are then called blank nodes. So let's recapitulate. We have basic URIs, which are accessible via the web. We have literals, which can be untyped or typed. And we have these special things called blank nodes. And these then are all the building blocks we need for encoding RDF. So as a next step, let's look at some of the so-called serialization formats in which RDF can be expressed before we look at all the possibilities you have with, formulating or representing knowledge with RDF. So first, let's have a look at the serializations. The most basic serialization, besides the graph serialization or the graph representation that we already know, are the so-called n-triples or the n-triples notation. So here, URIs usually are denoted within angle brackets. So these are these pointy brackets that you see here around the URIs. So if you have a URI, use angle brackets. If you're using literals, use quotation marks. We already did that. And usually, when your fact is over, so if you have subject, property, and object, the end of this triple is always denoted with a period. So it's pretty simple. You see here the two examples. First, Pluto has been discovered in 1930, period. And then the next one, Pluto has been discovered by Clyde Tombaugh. Okay, so this is the most basic notation. But of course, you can imagine that this, especially if many URIs are involved, is on the one hand rather lengthy, and on the other hand, it's difficult to read. So therefore, there is a more, let's say, concise notation. And this is the so-called turtle notation. This is the terse RDF triple language notation. And this is an extension of the n-triples notation. So what you could do here, for example, you can abbreviate these long URIs with the help of so-called prefixes. And you can also use angle brackets together with so-called relative URIs, which then are extended to a given base URI. So this is what you see here. We will talk about this in detail later. But you see here you have Pluto, and Pluto does not have the prefix here. It's simply put in angle brackets. So the base prefix that has been here defined previously, which is dbpedia.org/resource/ will be automatically endorsed and complemented here to that relative URI Pluto. And if you want to use a special vocabulary, so if you want to use a special prefix, like here we use the prefix for dbpedia ontology, it will be the prefix dbo that we define in the first line, and then this can be used as a prefix for other URIs that are here, for example, used in the case of the property. So this is some way to make abbreviations. And then, of course, you will agree, especially later, if we look on longer examples, that this is much more easier to read. Of course, if you try to implement a parser who reads that kind of notation, it will be more difficult. But for a human, this is pretty easy to read. And then, of course, if you exchange this kind of data among programs and applications, you for sure also need an XML-based notation. So this is a serialization of RDF based on XML syntax. So here again, you have to use a special namespace for RDF. And here is also a definition of a namespace for dbpedia ontology. So let's have a closer look on that. So where are our triples here? So first thing we are talking about, the subject here is the RDF about. So we have here an RDF description of a resource, and the resource we are talking about is here encoded within the attribute RDF about. So here you see Pluto, and this is our subject. Now, all of the properties we use here are using this second namespace, the dbpedia ontology namespace. Therefore, they here start with the NS0 prefix, and then you see here a tag which is called discovered, and then the literal 1930, and then the discoverer. So this here, discovered and discoverer, is the property, and then in blue here you see the objects. First one is simply a literal, so here it's embedded within the tag discovered, so it has a start tag and an end tag, and in between there is some text, and this usually then is the literal. Or the second one, this is a so-called object properties. There the object is a URI, and here I have to encode the URI either on the one hand, for example, as an anchor tag, or here as an RDF resource. This is usually to make clear that this is really an RDF object. Then I say the discoverer, and then I use the attribute RDF resource, and then I say this is the URI of the object. So Of course, we have to confess this is a little bit more difficult to read for a human, especially if you consider larger representations and not only these small ones we use here as an example. But on the other hand, every program that has an API that understands XML is able to pass this kind of data. So besides XML, there also exists another very popular representation form, which is based on JSON. So we have here, for example, a JSON LD. LD stands for linked data notation, which has been introduced with RDF version 1.1. So here, it's also rather difficult to read. So we see here the first part of the JSON stack. Here we have the resource Pluto. This is the subject, and then follows the properties here, first discovered and then discoverer, and then follows another section here which denotes the object, which is here, first case, a literal 1930 or a URI, which is here then Clyde Tombaugh. So you see this is a little bit easier to read, but for large files this will also become a little bit difficult. So in the course of the lecture we will stick to the turtle notation, which will be explained then in the next sections of the lecture. Okay, so in the next section of the lecture we will look at more details, or in more detail on RDF. We will learn how to express more and more sophisticated knowledge with the help on RDF, and we will serialize this then with the turtle serialization.